All right, so now we have the rule for integration by parts, and it says if you're integrating the product of a u and a dv, you can convert that into u times v minus the integral of v du. The goal is that v du is easier to integrate than u dv. So this looks really weird, but just keep in mind that u and v are both functions of x. So we're just trying to pick out a function that's going to represent our that we're going to call our u, a function that we're going to call our dv. The dv always includes the dx part because that's some sort of derivative. Okay, so u du. So you can organize this how you like. Some people have this really nice way of just you integrate one, you differentiate the other, and put it all together. I'm going to keep laying it out because I'm just in the habit of doing that, and it keeps it nice and organized for me. So again, we get to choose the u and the dv, so that's up to us. The rules are it has to take up everything we see there. So we have an x, we have a cosine of x, and we have a dx. So anywhere from, let's see, so the dv has to get the dx. That's not a choice. But from there, both x and cosine x could go to u. They could both go to dv. One could go to u. The other could go to dv. There's lots of choices. And this is going to come down to another one of those. As you're learning, you're just going to have to try something and learn to spot whether or not it worked. General rules. We want u to be something nice to differentiate because we're going to use a derivative to get du. We want dv to be nice to integrate, or find the antiderivative for. So looking at this thing, we could try both ways. So let's say we decide to try u equals cosine of x, and dv is going to be x dx. I said you could choose x dx to be either one of them and try that out, but it's generally not a good idea. The point is to split up the product. So put one factor in the u, one or more factors in the u, and then separate off at least one factor in the dv. Okay, so really what we're doing here is we're saying, just like with substitution, if u is equal to cosine x, then du dx, the derivative of u, is negative opposite of sine x. In all of these, we're just automatically going to end up moving the dx up, so we tend to just get in the habit of doing that in one step. For the dv going to the v, what we're thinking here is kind of like what we did in our little derivation of the integration by parts rule. We're going to say, okay, well, we could integrate both sides. The integral of 1 dv is a v. The integral of x dx is an x squared over 2. And we will eventually include our plus c, but at this point, it's okay to just leave it out for a while. So what I have right now, so again, here, let me mark this all off. I decided that this was going to be my dv, and this was my, not my d, my u. So we're going to take u times v, and we're going to get an x squared over 2 times cosine x, and then we're going to get a minus the integral of v du. So we're going to take those two, and we're going to say minus x squared over 2 times negative sine x dx. I strongly recommend just getting in the habit of moving those negative signs out in front right away. That tends to be like the worst part of integration by parts, is having lots of negatives crop up and cancel each other out, and people lose track of them. Okay, so I have found now that my original integral is equal to this new mess. And your question at this point should be, is the v du in fact better or worse than the u dv that I started with? And I would say this is looking worse. I still have a trig function. Now instead of having an x, I have an x squared. That seems, if anything, like it's going to be even harder to integrate. So I think this was a bad pick. That's how you can spot a bad choice on your integration by parts. Let me pick a bright color. So I'm going to say, change my mind. I don't like this one at all. And then I'm going to go back and try switching it up a little. So I'm going to pick out my u, my dv, And then I'm going to use those to find my v and my du. Okay, so last time I let cosine x go with my u and x go with my dv. So I'm going to switch it. I'm going to let cosine x go with my dx, and I'm going to let x be my u. That makes the left side really easy. If u is equal to x, then the derivative of u with respect to x is 1. And again, we'll get in the habit of just doing this automatically, so you don't have to write the du dx, but I find that people will write it and then kind of forget what's actually happening. So I just really want to make a big deal about the fact that you're saying u is a function of x, so I would take the derivative of u with respect to x, and then you can move the dx over. And then same idea here. To find v, I have to take the integral of both sides. The integral of 1 with respect to v is v. The integral of cosine x with respect to x is positive sine, cosine. Yes, that's the other thing that gets really tricky. At some point, almost everybody gets completely boggled in whether or not they need a minus when they're integrating one of their sine or cosine functions. It is inevitable. We've taken derivatives, we've taken integrals, it flip-flops which one gets a minus, it gets confusing. Okay, so now I can say, I'm going to write out the whole statement. The integral of x cosine x dx is in fact, according to integration by parts rule, equal to u times v, which is x times sine x, minus the integral of v du, which is going to be a sine x dx. And that, I believe, was definitely an improvement. I had this product, x cosine x. Now I just have to figure out the antiderivative of a sine x. That's way better. So your goal is to eventually get rid of the product. Sometimes that happens because you have one of your factors is polynomial and you can just take the derivative till it goes away. Sometimes it happens because taking the derivative of say, for example, a natural log function turns it to a 1 over x, and you can algebraically simplify what you end up with. So there's some different things, but that's your goal, is to try and turn the v du into something that's easy to integrate. Okay, so the x sine x is done. I'm just going to keep that there. That's part of the antiderivative. The antiderivative of sine. Okay, so the derivative of cosine is minus sine, which means I actually have to put a plus out there so that it stays negative. And here is where I want to throw in my plus c. So don't forget it, you still need it, but you don't have to write it down in every single step as you do integration by parts. The final step is fine. So the antiderivative of x cosine x is x sine x plus cosine x plus c. And you can try taking the derivative, your check, of x sine x plus cosine x plus c. And it can be helpful, again, just to spot what's actually happening a little bit more. So we're going to do a product rule here. Derivative of sine, oh wait, I'm going to do sine times the derivative of x, which is 1. And then x times the derivative of sine, which is cosine. And then the derivative of cosine is the opposite of sine. Whoops. Whoa. Don't mind me jumping around. Okay. Opposite of sine, the derivative of constant is 0. So you can see the sine x's drop out and I get x cosine x, which is what I was hoping. I asked, what do I take the derivative of to get x cosine x? And it is, in fact, x sine x plus cosine x plus c. Okay. I think that's it for that one. I'm actually going to keep this in this long video instead of making it its own. So I do have some tips that are in your activities packet if you've printed it off. When we're choosing u and dv, this is what I said, but I just want to make sure it's written down formally somewhere. We always want u to be something that gets less complicated, ideally, or worst case scenario, doesn't get more complicated when we take its derivative. I say always, but there are exceptions. That's what makes some of these integration techniques tricky, is there's always little exceptions. We're going to integrate the dv, so we'd love it if it got less complicated when we integrate. That doesn't generally happen, so we would settle for at least not getting worse. We don't want the dv to get worse when we integrate it. We don't want the du to get worse when we differentiate it. That's kind of a general rule of thumb. Other things to think about, we have to use up everything sitting in the original integral. So when you choose your u and dv, if you multiply them back together, that should give you everything you see in the original problem. There shouldn't be any pieces left out. This is the really important goal. We want v du to be easier than u dv, easier than what we started with. If it's not, we might have a problem. And then, yeah, so when you're choosing your dv, you have to be able to integrate it, but as much as you can get shoved in there to integrate is good. So without making it really hard to integrate, putting more into dv can be a good thing. And I'm actually going to sneak in an acronym that a lot of people like. You know what, I shouldn't write it over here because then I won't be able to write the, here, LIATE. This is kind of a rule of thumb for, this is for priority on you. Priority for choosing you. Okay, so L is logs. So generally people latch onto this. If you have an X in there, make it your U, and that's great, but there are things that we cannot possibly allow to be our dv because we don't know the integral. So those trump everything else, and the first of those is logs, the second is inverse trig. So if you have a log or an arcsine or an arctangent, something like that, that's going to have priority on being your U because you do not want to have to integrate that. A is algebraic. This basically means your polynomials. So if you have an x or an x squared or an x cubed minus x, that's a good choice for your u as long as you don't have log or inverse trig, because if you make it your u enough, and you can repeat integration by parts as many times as you need to get something simple for v to u. If you have a polynomial as one of your factors and you differentiate it enough, you make it your u and differentiate it enough, it's going to eventually become a constant. T is for trig functions. They don't have high priority on u because they're really easy to find antiderivatives of. And the same thing is true for exponential. So this is your priority list. Your ranking on what you should look for your u. So if you remember LIATE, it'll help you pick out u's. Okay, long one. Hopefully that gets you started.